So we're now going to move to our final presentation before break, and we're pleased to welcome to the stage Aldec. Now, unfortunately, Jacek, who was going to present, has been held up in Europe for personal reasons. So I'm going to hand over to our other presenter, Karthik. Do you want to make the introduction?
Yeah, hello. And today we have Ravi from Aldec who will be making a presentation.
Good morning, everyone. Myself, Ravi Kumar, working as a field application engineer in Aldec. So, I'm responsible for hardware-assisted verification, such as acceleration and emulation. So today we talk about SCE-MI, which is a standard co-emulation interface model, which is from Accellera, which is a standard from Accellera. So with using SCE-MI, you can actually reduce the verification bottlenecks. So you can have many advantages, like you can have faster simulation speed, and can reuse the test benches for both simulation and emulation, and you can cut down the time to market for any SoC. So looking to the agenda, so we have a little more information on the transactors, so which is the main part of the SCE-MI. So after having a word with the transactor, so we move on to the SCE-MI applications, where and all you can use SCE-MI. And last thing is customer case studies. So it may give you a clear idea on how you can use SCE-MI according to your design specifications. So basically, a transactor is nothing but a transactions, which is a bridge which converts transactions into a message-based, a message into a bit-level vectors. So as you can see, so if you go through RTL verification, so as and when the design complexity increases, you will simulate the design, but you'll get slower performance. So that's where the transaction come into picture, which is a higher level layer. So basically, one message can be transformed to can be given to the DUT with 100 clocks of bits of information. So with this higher abstraction layer, you will be getting faster design entry and faster simulation and reusable IP code. So with this, you can also have early hardware software integration, and moreover, the software engineers who are waiting for the drivers to be developed, they can actually proceed with the software development in the early stage. So basically, if you look at the transactor, if you want to implement a SCE-MI in your design, it has to be a synthesizable transactor, which will sit on the hardware part. So basically, the software application which gives a function call. In this case, I can see that do write of data is a function call which gives out to the hardware, which is sitting on the transactor, which is sitting on the hardware. So one message can be a sequence of many bits. So with this, you can have a faster simulation in your verification. So let us look into the types. What are the types that you can able to use in SCE-MI? So first one, we have a Macrobased, which is released in 2003. So which is a macro-based model. So after 4 years, they have released a function-based and pipes-based. So macro-based is like very closer to your RTL, and function-based model uses DPI calls in order to interact with the software and the hardware. So the pipe-based is not popular because user says it's complicated and it doesn't have any clear advantages. So let us look into the difference between macro and DPI. So basically, macro, if you look at it, so this is a lower level layer which is closer to the RTL, and you can have a full control on the clock for your DUT. So, so suppose if you want to simulate with a third-party simulator, you need to have a ALDEC SCE-MI sim. Okay. So coming to the function-based DPI, so it is very closer to the transaction layer, and this is an implicit clock control, and it's very easy to use because it can you can integrate with the system Verilog test benches. So let us look into macro-based model example. So here you can see there are two parts. One is software, one is hardware, which can be your prototyping board. So suppose if you need to develop a transactor which does this functionality. Basically, if you say a macro-based model, it has two parts. One is the software part, one is the hardware part. So hardware part consists of input and outputs, and software part consists of proxies. So in order to transmit data from test bench to the DUT, it uses input, and when we give test vectors to the DUT will respond to the test vectors, and it gives out the response back to the test bench through output. So this is about macro-based model. So let us look into the function-based model. So basically, so macro-based model uses ports, but in case of function-based model, it uses DPI to a function calls. So you can see that any transaction happening between test bench and DUT is made through a function call. So if we can, let's say the DUT is RAM memory, you want to write some data to the DUT, so you give a write function call, and if you want to read some data from the memory, you give a read call. So let's say test bench, which is you have already simulated. So now you want to prototype the. So if you want to prototype the design, you can actually go with the macro transactor. I mean, you can use both models, macro-based as well as function-based. So in order to use macro-based, you need to have a DPI call between system Verilog test bench to the thin C layer, and then a thin C layer is being communicated to the macro transactor. So on the other hand, the function-based DPM model uses DPI on both sides, from from the test bench to the thin C layer and thin C layer to the DUT. So one of the more important application is like testing against the executable specification. So if you look at a complex algorithm, so which you already have it in C, C++ or System C model. So now you have developed a RTL model. So now you want to check whether executable specification is matching with the hardware. I mean the DUT which is sitting on the hardware. So what you do is you try the same stimulus to both executable using SCE-MI transactor, and you give it to a comparator which will compare the both results, and you can verify the functionality on the fly. So this is where in this slide you will be able to see that how you can gain the time. so which can bring down the time to market. So for any SOC, time to market is very important. So as a traditional approach, you can see there are three stages. One is modeling, implementation, and integration. So modeling comes for the design engineers will be doing a modeling phase. Then verification engineers will be doing implementation. Then software engineers will be doing integration phase. So here, if you look at this slide, so they are a sequential one. So you need to wait until all the stages are completed. But if you use SCE-MI emulation in your design, as and when the model is being developed in the modeling phase, you give it to the implementation guys, verification guys. They will be putting the design into the hardware, and they will be checking for the bugs in the code. And meanwhile, you can have also have the integration facility so that software developers can write drivers for individual RTLs or the design. So ease of virtual prototyping. On the top slide, you can see that this is a traditional approach, and the bottom slide you can see the how SCE-MI can be used for virtual prototyping. So if you see a traditional approach, you have the hardware prototyping board, you have the design. You need to let's say this is a design digital camera, so which has three inputs. One is one from image sensor, another is output is a real LCD, and buttons or jog dials on breadboard. So you need to have cables to connect to the prototyping board. So if you use a virtual prototyping, so what you do is you create a virtual applications for all of these input and outputs. So here you can see that using a SCE-MI based model, you can have a virtual C++ or System C applications here, and you can connect to the hardware. So thereby you have no additional hardware for this type of input or outputs, and no cables are required in order to test the design. So let's say if you have a ARM processor, which is a DUT, right? And if you go for a JTAG, it will be very slow by design. So we have a vStream transactor which will connect to the ARM processor. It is basically meant for connecting to the processor so that you can have control on the processor, saying you can have breakpoints or stepping or stopping on the execution flow of the processor. So basically, the software and hardware is linked through PCIe communication. So as we know that TLM2 and OOP are evolving. So with this, we have a broad range of processors like ARM series, Xilinx series, and ARC and MIPS. So here in the software, you have TLM2 interface. On the other hand, you have peripherals like USB or any other peripherals. So this uses actual interface. Suppose if you want to connect between these two, we provide a TLM2 SCE-MI adapter, which will get you more interoperability. So next thing is a quick emulator, which is QEMU, which is used for pre-processor emulator with efficient binary translation. Here you can actually emulate any processors like ARM or Intel or any kind of a processor, along with peripherals such as network interface card or USB interface. So having this, you can tell to the software developer saying that you are ready with the design. You can test the drivers on the design. So we have a couple of customers customer requirements, and we have provided the solutions accordingly. So let us look into the first customer requirement. So they wanted a 3-stage based simulation and emulation strategies. So first they wanted simulation with UVM and emulation with SCE-MI transactors. Then they wanted in-circuit emulation along with the SCE-MI transactors. So for all of these strategies, they wanted to use the same C test. So duration of the project was 5 months. So we are using S7 with Vertex 7 chips. So this has more than 10 interfaces. So this is the design. So if you look into the architecture, it has multiple gigabit Ethernet and for fabric interface along with the PCI interface for communication. So this design is a multi-core design which has 32-bit processors. This was coming around 20 million ASIC gates. So first stage, during the first stage, we were trying to simulate with UVM. So as you can see, UVM driver is tagged to the actual RTL design using a virtual interface. So on the other hand, we have instruction set simulation. It's basically meant for the CPU breakpoint or stepping of these processors. So the C test is applied on the CPU so that it can process data to the individual modules. So next we have a transition. As and when the modules are ready, so we were, as and when the transactor ready for individual modules, we were actually bringing those modules onto the hardware. So which is emulator. Here you can see that, so in the previous slide you can see that module 2. So let's say module 2 has a SCE-MI transactor. So we brought this SCE-MI transactor along with the module 2 onto the emulator. So this is how it is connected during the simulation or in the emulation. So next we picked all the design onto the emulator. So this is when all the transactors for all the peripheral transactors are ready. So we connected all this design onto the board. Through a host machine, we were applying C test cases. So suppose, let's say, if we want to feed real world test vectors to the hardware, so we were connecting real world interfaces, let's say Ethernet, C6, or JTAG cable. So with this, we were able to do full-fledged prototyping. So this is the new board which we have released. This has a Vertex 7 board. So this can be configured we have a configuration of simple or dual chips. So here it has a SATA interface, PCI Express interface, USB interface. It has many other interfaces, and along with the connections which can be connected to the daughter board. So as and when, so in the previous slide, it can support 12 million to 24 million depending on the chip configuration. So here you can see as and when if the user wants more design complexity, so we have a backplane board which consists of 4 Vertex S7 series board, which can be stacked on the backplane board. So you can get up to 96 million gates. So this is a customer B requirements. They wanted to use a full-fledged emulation, and so they were having third-party prototyping boards. So this is the block diagram of the system on chip which they were using. This is actually they were using dual-core ARM processors. So they wanted to check the peripheral interaction with the processors. So this design is having 30 million ASIC gates. So in the initial phase, we connected. So this part, which is shown in the blue, was an emulator. On the other hand, you can see the system C test bench, which is sitting on the host machine. We were running the system C test bench to the emulator, and we were seeing the functional results. So on the top, you can see JTAG is connected to the ARM processors to control the execution of the processor. So later, we removed the JTAG cable, and we connected the JTAG transactor in order to have a full visibility on the processor through Eclipse or GDB. So on the final stage, we removed System C test bench, and we had TLM virtual platform, so where it has a peripheral subsystem and multimedia system through TLM bus and a transactor, which is connected to the XE bus of the whole SoC. We were doing the emulation. So apart from this, we have support for third-party prototyping boards, which can be reused for emulation, simulation, acceleration, and prototyping. So you can see that you can have multiple vertex 6 FPGAs, and you can also have 16 vertex 5 FPGAs, which is having a PCI Express bus. So with this, you can have a better return on assets, and you can reduce the time to market. So, and also you can reduce verification bottleneck. So with this, I want to close the talk. And if you want to have the clear full-fledged demo, you can visit the Aldec stall. You can I'll be presenting the demo for Aldec, acceleration and emulation. Thank you.
Thank you. So we have some time for questions before we go to the break. So I'm going to have to run around so you can get the microphone.
Yeah, myself Imtiaz Sheikh from Infineon Technologies. I have a couple of observations here. So first observation I have in your presentation is you are talking about transactors which should be synthesizable in nature. So my question is, if the transactor has to be synthesizable in nature, definitely the amount of development time it will be required, that will be definitely huge, and I'm sure this will add to the verification cycles, especially in the timing requirements, because development of such transactors will take huge amount of time. And in earlier presentation also we have seen that the kind of developments happening in the design from one protocol to other protocol or one version to other version, those are tremendous. So reusability of such kind of transactor is questionable. And second observation I have is when you say that these transactors are synthesizable in nature and those will be written using the same way like normal HTL development languages, I have to say that then they are equally prone to the bugs which we are trying to find out in our verification. What is the guarantee of these kind of transactors that they are bug-free and they can be effectively used for the verification?
The first question was, the transactor which are synthesizable, how I can reuse, or what is the amount of time that you are developing for the transactors? For this question, we have already already developed transactors. Let's say if you want to use OCP protocol in your design, we have OCP, I2S, I2C, SPI. So we have ready with the transactors. You can actually use the transactors which are available from Aldec. Okay. The second thing is it a bug-free? The transactor is bug-free, right? So we have given to the customers which are Intel, Qualcomm. They have used the transactors. They have gone through the transactor verification and functional verification. They say that it's fine. So that's all.
Okay.
I'm not satisfied with your answers because, again, I mean, say for example, I'm verifying PCI Express 3G, and you have transactor for PCI Express 3G, and I have $1,000 in my design. I'm sure there will be $1,000 in the transactor also. I mean, what's the guarantee that the transactor is bug-free? There is no doubt. On top of that, there will be huge amount of dependency if I'm going for a specific, say for example, ALDEC transactor. I mean, if I have 3G protocol, if 4G is coming into the picture, I'll have to totally rely on ALDEC's availability for these kind of developments. So how reliability is questionable in that case?
Maybe we can take this offline. We'll be able to answer your.
Okay, thank you. We have time for another question. Do you want to introduce?
Hi, I'm Pushkar Naik from Applied Micro. My question is, you have shown the software side and the hardware side in this. Now, how does it really synchronize? Because the hardware is going to race ahead, and especially when there is too much of to and fro action going on, do you really achieve anything doing this emulation?
Yeah, the data communication between software and hardware is defined in SCE-MI standard. If you go through the SCE-MI standard, they will be defining how the data transfer is happening.
I know the standard. My question is, do you really, I mean, in real life, when there is too much of to and fro action going on, do you really achieve in terms of time? Because the hardware will be held up until the software gives you commands, which is much slower in nature.
Okay.
There's a question to you. So, have you really seen a speed advantage when it comes to too much of to and fro action?
There's another one from Aldec. Godfrey.
I'm from Aldec. Let me answer this question because we just handled few cases in India. We are experts from Aldec Poland. Maybe we'll forward your questions to Aldec Poland and we'll get back to you. Okay, you can maybe give your email address or business card and we'll come back to you. Thank you.